The LFP Short Blade Battery is recognized for its enhanced safety features, including improved performance during fires and reliable operations, even in temperatures below 30 degrees Celsius. Engineered to sustain over 1 million kilometers of driving over a span exceeding 50 years, what factors contribute to ensuring such high levels of safety for this battery? Why is LFP Short Blade Battery technology considered the superior choice in terms of safety? The Short Blade battery, shaped like a unique long sword, is a cell-to-pack technology where cells are directly integrated into the battery pack rather than grouped into separate modules beforehand. This enables higher energy density at the pack level. Companies like BYD, S-Volt, and Geely are leveraging Short Blade batteries. While Geely primarily uses batteries from suppliers for its electric vehicles and also partners with CATL, Ferasis Energy, and LG Energy Solution, it's also developing its own batteries. The Aegis Short Blade battery is among the latest advancements in this effort. During testing, these Short Blade batteries have achieved 3,500 charging cycles, equivalent to driving and recharging for 1 million kilometers. This minimizes battery degradation, prolonging useful lifespan and enhancing residual value for older electric vehicles. Additionally, it claims to reduce carbon emissions by 80,000 tons annually, roughly equivalent to a typical car driving 20,000 kilometers a year over 50 years. This new type of battery effectively addresses internal resistance issues commonly found in longer blade versions by using thin, long nanocarbon tubes to facilitate ion transmission and incorporating additives to improve permeability, enabling faster charging. With an energy density of 192 watt-hours a kg, an average charging rate of 2.45, and a lifespan of 3,500 cycles with minimal capacity loss, it reportedly charges from 10 to 80% in approximately 17 minutes and 4 seconds. The Chinese company also provides a comparison. Quoting from test data, Geely cites an average charging time of about 26 minutes from 10 to 80% and an average charging rate of 1.61 C for blade batteries of the same capacity. However, these values have not been independently verified. This achievement can be attributed to the use of long, thin nanocarbon tubes in the battery to facilitate ion transmission, along with additives to improve membrane permeability. These changes help lithium ions move more easily between electrodes, thereby enhancing fast charging performance. Currently, it's still unknown when these battery cells will be mass-produced. Emphasis on cell safety remains paramount, utilizing high-durability membranes, stable thermal characteristics, and self-bonding technology designed to prevent short circuits and thermal runaway. To achieve this goal, Geely has conducted extensive tests on the batteries, including 8 nail puncture and military gun shooting tests. According to Geely, no negative impacts occurred during these tests. On June 27, 2024, in Hangzhou, Geely Auto Group unveiled their latest self-developed generation of short-blade lithium iron phosphate batteries, offering best-in-class battery life, charging speed, and optimized safety. Geely's new Short Blade EV battery technology sets a new standard in the EV battery industry with top safety features, compact size, higher energy density, improved volume utilization, and enhanced flexibility to adapt to various pack designs. Regarding safety, Geely announced on-site that the safety test results of the Aegis Short Blade battery at the China Automotive Industry Testing Center's New Energy Testing Center. Testing included core penetration, immersion in corrosive seawater, dropping and severe impact on 3 sides of the battery, external battery fire tests, vehicle side impact tests, front underside scraping tests, rear underside scraping tests, vehicle underside scraping tests, etc. All battery safety test categories exceeded significantly national standards. Geely's new Short Blade EV battery technology incorporates their self-developed self-bonding technology on the electrode surface to prevent short circuits in case of accidents. If a battery cell punctures during severe collisions, a layer of aluminum foil integrates into the battery membrane to create an insulating layer, preventing short circuits and uncontrolled thermal events. How did the tests of the Short Blade LFP battery exceed industry standards? Until now, the standard automotive test for EV battery safety performance was the single needle puncture test. However, Geely Auto conducted a bold experiment by testing the new short blade battery technology with 8 simultaneous needle punctures, increasing the damage sustained in extreme collision scenarios. During testing, it was punctured simultaneously by 8 steel needles, each 5 millimeters in diameter, and left undisturbed for an hour without any adverse effects. In addition to passing the 8-needle puncture test, Geely subjected the new short blade battery technology to the industry's first 6 extreme limits tests, including immersion in corrosive seawater, extremely cold environments, high-frequency bottom scraping of the battery pack, 26-ton overload rolling, side impact on a single battery pack, and fire roasting. With its patented mesh frame design, energy absorption chamber, 3-layer sandwich bottom protection plate, integrated CTB, thermal runaway control system, and other safety features, the battery pack successfully passed all 6 tests. Testing the new short blade EV battery technology under conditions far exceeding industry standards, results showed no thermal runaway, smoke, ignition, or fire in any scenario. Additionally, the insulation resistance values of the battery electrodes and the sealing condition of the cells remain normal. The results demonstrate that the new short blade EV battery is safe and reliable even in the harshest conditions. The battery has passed an additional 6 extreme tests, including immersion in corrosive seawater, extremely cold environments, high-frequency bottom scraping of the battery pack, 26-ton overload rolling, side impact on a single battery pack, and fire roasting. These tests were conducted by the China Automotive Center, and Geely's battery passed all of them. These tests meet higher standards than national requirements, and in the scraping test, 3 repetitions were required. The rolling test endured a weight of 26 tons. The cold weather test withstood minus 35 degrees Celsius at an altitude equal to 5,000 meters for 8 hours, and the fire test endured 1,000 degrees Celsius for 130 seconds. Such results are achievable because the short blade battery uses a high-strength, thermally stable, high-temperature resistance separator, combined with stable separators and safe electrodes to create higher energy density and safety. Additionally, there's a self-bonding technology on the electrode surface that prevents short circuits in the event of an accident. A layer of aluminum foil integrates into the battery separator to form an insulating layer if the battery cell experiences severe shock and puncturing. Geely stated that the battery features a patented mesh frame design, energy absorption chamber, 3-layer sandwich bottom protection plate, integrated cell-to-body, thermal runaway control system, and many other safety features. How can the short blade LFP battery ensure safe driving for 1,000,000 kilometers? Good question. As previously mentioned, the cycle life of the new short blade EV battery technology can reach up to 3,500 cycles. That's equal to charging and driving for 1,000,000 kilometers with minimal impact on the battery's range. The use of multi-element doped electrode materials combined with a smaller size and lower internal resistance of the battery reduces the internal chemical reaction rate, and that extends the battery's lifespan. On top of that, thanks to its ultra-fast charging capability and stable performance at those low temperatures, the new short blade EV battery technology addresses the high internal resistance issue commonly found in long blade batteries that are on the market. Geely's latest battery also uses long, thin carbon nanotubes to create highways for ion transmissions and additives to improve membrane permeability, allowing lithium ions to move more easily between electrodes, thereby enhancing fast charging performance. Test data shows that for blade batteries of the same capacity, the average charging time from 10 to 80% SOC for long blade batteries is about 26 minutes at an average charging rate of 1.61 C. With the new short blade EV battery technology, that average charging time is 17 minutes and 4 seconds, with an average charging rate of 2.45 C. Furthermore, in extremely cold environments, the new electric vehicle battery technology offers stronger discharge capability and longer driving range compared to long blade batteries. At an ambient temperature of minus 30 degrees Celsius, the average capacity retention rate of long blade batteries drops to 78.96%, while the new short blade EV battery technology maintains 90% capacity. The shorter length, approximately 40% shorter than conventional long blade batteries, results in less internal resistance and heat, while volume utilization increases by 50%. The release of Geely's new generation Blade battery is undoubtedly a major breakthrough in the EV industry. It not only improves the performance and safety of electric vehicles, but also sets a new benchmark for the whole industry. We also hope the industry will truly shift from roll-to-roll to roll-to-pack technology. What are the outstanding advantages of the Shortblade LFP battery compared to other lithium-ion batteries? The technology I want to mention here has an energy density of 192 watt-hours a kilogram, comparing with other lithium-ion batteries that are on the market, including current LFP types. Energy density is crucial for batteries because higher energy density allows for lighter or smaller batteries that still provide good capacity, thus reducing the weight of electric vehicles and making them more efficient, thereby increasing their range. Lowering the weight of EVs, increasing their range, and increasing the energy density of batteries enables the battery pack to perform well while still being lighter or smaller, thereby continuing to increase the operating range. Traditional LFP batteries do not have high energy density, but newer technologies such as those from Geely have quite impressive energy density. When compared to other battery technologies on the market, this battery has a power of 192 watt-hours a kg, lower than the nickel battery. For example, the 2170 battery made by Panasonic found in the Model Y has an energy density of 263 watt-hours. In addition, Tesla's Cybertruck has an estimated energy density of 256 watt-hours. It's clear that nickel-based batteries have higher energy density. However, when switching to other LFP battery technologies like BYD's Blade battery with a cell-level energy density of about 168 to 175 watt-hours a kg, and CATL's prismatic LFP battery that's used in the Model 3 rear-wheel drive with a cell-level energy density of about 160 watt-hours a kilogram. Thus, the 192 watt-hour a kilogram energy density of Geely's LFP battery is quite impressive compared to the competing products on the market. More importantly, the ultimate energy density at the pack level is more crucial. We do not have the precise figures for Geely's new battery technology regarding how efficiently it is packaged. However, from what we can see, Geely has designed these cells to operate in a monolithic battery format, meaning that they do not require additional packaging with modules. Additionally, this battery has a cylindrical shape, which can be used in a battery pack structure, aiding in efficient packaging. Therefore, we hope that when these battery packs are installed in electric vehicles, they'll have the packaging efficiency compared to the Blade battery. The energy density of the Blade battery at the pack level is pretty impressive. We expect that Geely's new battery pack will have similar pack level energy density, leading to an increased range compared to other battery technologies. We're really looking forward to seeing Tesla use these batteries. For instance, in the Model 3 rear-wheel drive, we believe this will allow the car to have a range of over 300 miles. On top of that, BYD is also preparing to release the next generation of the Blade battery soon. Although we don't have all the details yet, it seems that this battery technology will have a cell-level energy density of around 270 watt-hours a kilogram and a pack-level energy density of about 190 watt-hours a kilogram. However, this battery will be lithium manganese phosphate LMFP and not as long-lasting as conventional LFP batteries. With Geely's battery, its lifespan could be longer. In a press release in June, Geely mentioned that they use multiple doping elements in the electrode materials combined with smaller particle size and low internal resistance, which helps extend the battery's lifespan. This means that Geely's enhanced the electrodes by adding additives to improve performance. And that's a common practice in the battery industry used to achieve desired characteristics like faster charging or a longer lifespan. What Tesla model is best suited for short-blade batteries? Integrating the LFP Short Blade Battery into the Tesla Model Y Juniper for 2025 presents a lot of advantages. Designed for optimal performance, range, and efficiency, Model Y Juniper could benefit greatly from the characteristics of LFP's Short Blade Battery. One of the most compelling aspects is its impressive fast charging capability. Compared to the current Tesla Model Y 2024, which supports up to 250 kilowatt DC fast charging, charging from 10 to 80% in under a half hour, the LFP Short Blade by Geely offers significantly faster charging times, reducing the charge duration to just 11 minutes. This stark difference highlights the potential of the LFP Short Blade to enhance the user experience by minimizing charging downtime. In contrast to Tesla's current battery technologies like the 2170 and 4680 cells, the LFP Short Blade stands out in the LFP segment with its high energy density and innovative compact design. while Tesla's nickel-based batteries, including both the high-density 2170s from Panasonic and the newer 4680 cells out of Giga, Texas, boast impressive energy densities of around 263 to 244 watt-hours a kilogram respectively. And that has the LFP Short Blade staying competitive within the LFP category due to its compact design and robust energy density. This makes the LFP Short Blade a formidable contender, particularly for applications that require higher energy density and improved thermal management. Moreover, considering the broader implications across Tesla's lineup, the potential adoption of the LFP Short Blade extends beyond the Model Y Juniper. Tesla could leverage this technology in other models, enhancing their charging efficiency and operational capabilities. For instance, integrating the LFP Short Blade into models like the Model 3 or Model S could similarly improve fast charging capabilities, thereby increasing appeal to a wider range of consumers looking for both performance and convenience in electric vehicles. Not only that, integrating the LFP Short Blade battery technology into upcoming Tesla models like the rumored Model 2 could revolutionize the EV landscape further. The potential adoption of this advanced battery in a compact and affordable model like the Model 2 could significantly enhance its market appeal. For the Model 2, known for its anticipated compact size and affordability, the LFP Short Blade battery could offer several advantages. First, its high energy density and efficient thermal management would allow the Model 2 to achieve a competitive range on a single charge. This would address one of the critical factors influencing consumer adoption of electric vehicles, and that is range anxiety, by providing ample driving range without compromising on performance. Moreover, fast charging capabilities of the LFP Short Blade would be particularly beneficial for urban commuters and city dwellers, which often require quick top-ups during the day. With reduced charging times, potentially similar to those seen in Model Y Juniper, the Model 2 could offer a convenient and practical solution for daily driving needs. From a manufacturing perspective, LFP Short Blade's innovative design could streamline production processes and reduce costs associated with battery pack assembly. This aligns with Tesla's goals of scaling production efficiently while maintaining high standards of quality and performance across its vehicle lineup. Furthermore, the introduction of the LFP Short Blade in the Model 2 would align with Tesla's strategy of sustainable transportation. By offering a more affordable EV option with advanced battery technology, Tesla could expand its customer base and accelerate the global transition to electric mobility. In conclusion, the integration of the LFP Short Blade battery in the upcoming Tesla models like Model 2 holds promise for the reshaping electric vehicle market. It not only enhances driving range, performance, and fast charging capabilities, but also reinforces Tesla's leadership in innovation and sustainability within the automotive industry. This strategic move could set new standards for compact EVs, making them more accessible and appealing to a broader audience of drivers across the globe. The strategic adoption of the LFP Short Blade battery not only underscores Tesla's commitment to advancing battery technology, but also sets a new benchmark in the EV industry for fast charging capabilities and operational efficiency. This move could further solidify Tesla's position as a leader in sustainable transportation, offering enhanced performance and convenience while contributing to broader adoption of electric vehicles worldwide. We hope you'll experience the utmost relaxation after watching this video. If you do, hit the like button and join the Tesla Car World community by subscribing to our channel. Press that notification bell icon and stay tuned for any fantastic videos coming your way. Your feedback and time are highly appreciated. We all know that the Tesla 4680 battery is currently the most advanced battery that Elon has for his Tesla EV, but speaking quite frankly, it can't be denied that it is not yet impressive enough to surpass potential batteries like Toyota and Volkswagen's solid-state batteries. However, that's going to change soon as Tesla's aiming for the 4680 battery Gen 3 with at least 2 crazy changes that'll make it the leading battery technology in terms of chemistry. Of course, if Tesla succeeds. So, let's get into what is this 4680 battery Gen 3 change. You may not know yet, but 4680 batteries has actually gone through 2 generations, initially in the Model Y, but it was not very efficient, so Tesla took it out to go back to using the 2170 and LFP. Right now, 4680 cells currently being made at Giga, Texas are the 2nd generation, which have a 10% higher energy density than what they use in Model Y. They're called Cybercell because they're mainly used for the production of Cybertruck, with a 123 kilowatt-hour battery pack size consisting of 1,344 battery cells. Although it does provide quite good performance, it's clearly not enough, and Elon realizes this is not the final destination of this battery technology. So some recent reports announced that Tesla will soon produce the next generation of the 4680 battery to form a complete version, and we call it Gen 3. If we say the 4680 Gen 3 battery will make the Cybertruck or any future model integrating it cheaper and more powerful, you might not believe it, but that's soon going to become a reality. Let's take a look at the first major change that makes it significantly cheaper. The 4680 Gen 3 battery utilizes Tesla's dry electrode coating process. 1. What is 4680 battery dry coating electrode, and why does the 4680 battery need the dry coating electrode? Okay, to recap, Tesla first introduced 4680 cells at Battery Day back in 2020, confidently stating that this type of battery would give 5 times the energy and increase the range by 16%. But it's not clear if it has yet reached that level of performance because Elon has not yet been able to uniformly apply dry coating to both the anode and cathode of the 4680. Until now, battery electrodes have mainly been coated using a process called the wet coating process. This process involves mixing a powder mixture of active materials with solvents and other chemicals to form a slurry, resulting in the slurry then being coated onto foil, which is rolled to create the cylindrical cell. The electrodes are then dried in very large ovens that are tens of meters long and increase the plant area, energy consumption, and processing time very slowly. And that makes them pretty expensive in tons of different ways. We also need to note that the 4680s Tesla's currently using in the Cybertruck are a hybrid type. The anode is dry coated, but the cathode is not, resulting in the cathode accounting for over 35% of the total cell cost. Tesla still buys from suppliers like LG, where they're coated using the traditional wet process. Producing the cathode with a dry coating is the most challenging part, but it also is the biggest lever to reduce costs. With dry coating, the mixing process is no longer necessary, nor is the substantial energy consumption of the expensive ovens. Using a dry electrode coating process, this means going directly from powder to film. This technique removes the entire step of adding and removing solvents, and it allows Tesla to achieve 10 times reduction in factory footprint and a 10-time reduction in energy consumption, and that's a massive reduction in investment. 2. How did Tesla achieve dry coating for both the anode and the cathode of the 4680 battery? Of course, Tesla couldn't do this alone, so Elon initially acquired Maxwell Technologies. They're a company that's claimed to have invented the dry coating process for manufacturing supercapacitors. But Tesla wasn't interested in supercapacitors. They primarily wanted the rights to the dry coating process to make the 4680 Gen 3 batteries. However, due to some limitations related to production speed, Tesla sold Maxwell, but Elon retained the intellectual property rights related to the dry electrode coating and kept a few teams familiar with this technology. Among them was a world-leading expert in dry electrode manufacturing technology. And ultimately, Tesla had to internalize this process at its own factory. So, was Tesla successful with the dry electrodes? According to revealed sources, Musk asked the battery team to cut costs by the end of the year and develop one of the most important improvements at the time, possibly referring to the dry coating of the cathode. The info cites 3 informants. 2 of these sources also said Elon might abandon battery cells if the issue isn't fixed by the end of the year. But the good news we've received is that a report from China claims that Tesla did finally resolve the dry cathode coating process, paving the way for a major cost reduction for its 4680 cells. This allows the company to make both anodes and cathodes using dry coating technology. The report also states Tesla plans to mass produce and install 4680 cells with dry electrodes for consumer vehicles by the end of the year. This info has been cited by people said to be familiar with the matter, and it's also been confirmed by the Chinese publication Late Post. Although this process was perfected in 2022 and proven successful in the lab, scaling it up for production has been a nightmare with dismal yields. According to a report by Late Post, the issue is that the dry-coated cathode rollers kept breaking down because the cathode material is much harder than the anode material. Each breakdown led to 45 days of downtime, contributing to increased costs in Tesla's battery division. The solution was to replace the equipment with better machines, but this required additional expenses that Tesla's management did not approve of at that time. However, Tesla eventually figured out how to produce a battery anode using the dry process. This is crucial because, as mentioned, the cathode part of the battery is usually a lot more costly than the anode. Therefore, producing the cathode using the dry process will significantly cut the production costs of Tesla's 4680 batteries. 3. How will the energy density of the 4680 Gen 3 battery increase? When the Maxwell Technologies acquisition happened, Dr. Maximilian Holland wrote that Tesla's 4680 battery cells cost around $100 a kilowatt hour, but dry cell electrode manufacturing technology is expected to cut the cost of the cells by 10 to 20% compared to traditional wet cell manufacturing techniques. So, if Tesla is as successful as reported, the 4680 batteries are now a lot cheaper, at about $80 a kilowatt hour, close to the price of the cheapest LFP battery cells currently on the market. Dr. Holland also said that with a successful dry electrode process, Tesla's going to save time, and the environmental benefits will also bring significant other benefits, along with some other performance benefits that Maxwell alluded to and Tesla is certainly keen on, because these benefits include energy density hitting 300 watt-hours a kilo compared to 500 watt-hours a kilo instead of 232 to 244 watt-hours per kilogram like the Cybercell has in the current Cybertruck. So, how does the energy density of the 4680 Gen 3 battery go up? It seems Tesla will indeed begin producing the 4680 cells by the end of the year using a dry electrode process that they've been researching for about 3 years now. Those familiar with the matter indicate that Tesla will mass produce and install 4680s with dry electrodes in consumer vehicles by the end of the year. However, the upcoming Gen 3 version of the 4680 will not only feature an improved dry-coated cathode for better efficiency, but the Gen 3 cells may also incorporate new chemical changes. Now, this might not happen at the same time, but another report indicates Tesla's figured out how to produce next-gen 4680s rich in manganese, which lasts a lot longer and has a much higher energy density. Right now, the cathode of the 4680 Tesla cell battery is NMC811 with 81% nickel, 12.4 cobalt, and 6.6 manganese. This means that in the upcoming Gen 3 update, manganese will be prioritized in higher terms. Tesla might have figured out how to make manganese-rich battery cells last longer with doped cathode active material. Manganese-rich cathode active materials like LiMn204 have long been considered an interesting option for their low-cost, high-voltage, and relatively low environmental impact. But they haven't been seriously considered for EVs due to the tendency for rapid degradation. Now Tesla has patented a new doped manganese-rich cathode active material that it claims to have increased the longevity of those battery cells. In the patent application, Tesla says that its doping of the materials results in better capacity retention at 50 cycles than regular manganese-rich cathodes. 50 cycles, that's still nowhere enough for electric vehicles, as it would represent about 12,000 miles of driving. That said, 94% capacity retention at 50 cycles, that's still a good sign as degradation often slows down, and therefore, the battery could still have decent retention at much higher cycles. Back in 2022, Elon said in regard to manganese, manganese is an alternative to iron and phosphorus for scaling cathode production to several terawatt-hours a year. Manganese also requires less lithium, and it operates at a higher voltage. However, as far as we know, manganese batteries lose capacity faster, and researchers are trying to make them more durable. You might wonder why Tesla would want to use manganese-doped cathodes in their 4680 Gen 3s, despite such a huge drawback. The main reason is that energy density is much more important to Elon in achieving a crazier driving range than what the 4680 Gen 2 is currently offering. Switching to a higher concentration of manganese improves the energy density in the battery cells and increases the driving range without additional cost for Tesla. And that's the main reason why Elon values this. If Tesla can mass produce these new 4680s using both dry anodes and cathodes and increase energy density by using manganese doping, it will make 4680 battery cells truly stand out. This is an exciting development that could lead to the wider use of manganese-rich active cathodes. We'll have to wait and see how powerful the 4680 Gen 3 battery will be with this improved chemistry. So, what has Tesla done to test the 4680 with both dry anode and cathode electrodes? Naturally, they've installed it in the Cybertruck. 4. 4680 Gen 3 battery real-world testing. It's no longer an exaggeration when Tesla, in their second quarter 2024 update letter, along with their second quarter earnings call, Lars Moravi said Tesla had successfully built the first Cybertruck test vehicle with a 4680 Gen 3 battery using the dry cathode manufacturing process at a mass production facility, which is a major milestone. That means Tesla has been able to mass produce 4680 battery cathodes using the dry process, something Maxwell Technologies had previously attempted to do before Tesla took over. But it doesn't stop there. And surprisingly, we also get to see the first real-world dry cathode validation testing of the Cybertruck. Joe Techmeyer, the resident Giga Texas drone operator, recently took to the skies above the factory and noticed a nice black-wrapped Cybertruck with a blue logo. Joe made this observation in passing. However, Tesla's head of the 4680 program, Bonnie Eggleston, responded by writing, "Nice shot of the dry cathode Cybertruck." This marks our first look at the dry cathode 4680 Tesla Cybertruck. From the outside, it might look just like another beautifully wrapped Cybertruck, but as we talked about, it's a one-of-a-kind special Cybertruck. When fully ramped up, this Cybertruck will be hundreds of thousands of dollars cheaper to produce than the current Cybertrucks on the roads. This might not seem like a big deal for a $100,000 truck. However, automotive profit, as Elon likes to say, is a game of pennies. There are 100,000 unique parts and processes, and if you can take out a penny cost from every step, you're increasing your profit by thousands of dollars. However, with the dry cathode process, Tesla is able to remove hundreds of dollars from Cybertruck's price by improving upon a single component and process. And that is truly a major advancement because not only is Tesla testing the battery cells in a Cybertruck, but they're also making these cathodes on mass production equipment. That means they've successfully achieved mass production of 4680 cathodes using the dry process, and that significantly cuts manufacturing costs compared to the traditional wet process. Tesla plans to begin mass production of the 4680 batteries with dry process cathodes in Cybertruck by fourth quarter this year, and this will reduce battery production costs, helping Tesla cut their costs lower than its suppliers. More importantly, with a cheaper battery pack, the pickup truck's price will likely go down without compromising performance. And that's great news for those of us looking to own an off-road vehicle this year or next. Current 4680 battery production progress. If there's an automaker known for accelerating production speed and processes globally, it's undoubtedly Tesla. Recently, not only in electric vehicles, but also in the production process of the 4680, Tesla achieved several notable milestones second quarter this year. In their second quarter 2024 update letter, Tesla noted that they were able to make 50% more batteries in second quarter compared to first quarter. 4680 battery production increased dramatically second quarter, resulting in 51% higher sales than first quarter, while significantly reducing the cost of goods sold. Tesla's now making over 1,400 4680 cell Cybertrucks a week. But that's not the end of the line, as Tesla will continue to ramp up until costs are at our cost parity target by year end. In summary, Tesla's doing very well in ramping up the production of 4680 batteries and addressing significant technical issues. We think 2025 is going to be a breakthrough year for Tesla's 4680 battery production, and their engineers will be able to focus more on improving performance and energy density of the batteries in the future. This is important and extremely exciting. Once the production of 4680 cells gets stepped up, it's no longer going to be a surprise if dry electrode batteries will also be deployed for other new models of the company. Manganese can likely be used with a small amount of nickel and cobalt. There will be less nickel and cobalt in this new Gen 3 4680 battery. Elon Musk is not just focusing on developing a battery with higher energy density for long-range vehicles. His goal is to provide a lower-cost battery that still delivers the same performance. The demand for lithium and nickel is very high, while the demand for manganese, not as much. Incorporating manganese batteries into production will help cut battery manufacturing costs. Research on batteries will continue and may never stop. If Tesla can reduce battery costs by a couple $1,000s and surpass LFP batteries in cycle life, then manganese battery chemistry is going to be very meaningful. There was a recent report from Reuters or another source saying LG will beat Tesla in producing dry electrode cells, meaning that making 4680 cells using the same dry electrode process as Tesla. However, this is unlikely and just typical misinformation about Tesla, as that's not expected to happen until 2026 or 27 at the earliest. It seems Tesla will actually begin producing 4680 cells using the dry electrode process they've been researching about for the last 3 years by the end of this year. The dry electrode process for the cathode is considered the most challenging part of the 4680 battery cell and the highest cost component, accounting for over 35% of the total cell cost. Therefore, we need to emphasize again how significant it is that Tesla can cut the cost of 4680 cells by around 30% while also improving energy density throughout the dry cathode. Truly a game changer for Tesla. Of course, there's always going to be minor issues that come up during large-scale production, especially in early stages, but it's clear Tesla's going to ramp up very quickly. Moreover, it seems they have a scalable process for producing the Gen 3 4680s for the next generation of electric vehicles. This is also significant because Tesla has years of experience, not only from their own efforts, but also from the technology they got from Maxwell Tech. Therefore, the Tesla team is confident that they have a scalable process by early 2025, and that also gives us lots of confidence. Tesla's success with 4680 Gen 3 is a major leap forward. Demonstrating their battery technology should never be underestimated. They are improving day by day, month by month on every production line. The 4680 battery stands out more than Toyota's solid-state batteries, which have been heavily hyped. While the 4680s made real-world progress, Toyota's solid-state batteries are increasingly becoming more mythical. This achievement not only affirms Tesla's superiority in battery technology, but also lays a solid foundation for future advancements in the future. So, what do you think about the new success of Tesla's 4680 next-gen battery? Let us know in the comments below. We hope you did learn more about 4680 batteries' big upgrades after watching this episode. If you did, hit that like button and join the Tesla Car World family by subbing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. Tesla has identified and resolved the bottleneck issue in the 4680 battery production, aiming to reduce production costs by up to 20% compared to current suppliers. The 4680 battery, get this, has the capability to support over 1,000 Cybertrucks every week, and that hits 50% growth and it cuts wait times. If this is successful, 4680 batteries are going to become the lowest cost domestically produced battery in the States. How has Tesla addressed the 4680 battery issue to create a significant shock industry-wide? What challenges is the 4680 battery facing at the moment? Earlier, Tesla's 4680 faced significant criticism, partly due to Tesla's bold claims. They had acquired dry cathode technology from Maxwell Technologies for nearly $320 million. Initially, the technology didn't work, meaning that Tesla spent years trying to make it work. However, they eventually attained success a couple weeks back, or around a month ago. Media reports suggested that LG Chem had beaten Tesla out in dry cathode production, but I don't recall whether it was either LG Chem, maybe it was Panasonic, or it could have been Samsung. Reading the news, we found it pretty funny because LG Chem, Samsung, and Panasonic have not yet started making those dry cathode batteries. Media likes to report inaccurately. Fake news, anyone? So you can't really rely on them to get the full scoop. Currently, in the Cybertruck, the battery energy density is at 256 watt-hours a kg, and that's a big-time improvement over the first-generation battery, but still lower than the estimated density of Panasonic's 2170 that's being used right now in Tesla's Model Y. The previously mentioned 54% range increase is directly related to the improvement in energy density, not only at the cell level but also at the pack level. Specifically, 40% of this increase comes from improvements in the battery's energy density. The remaining 14% relates to the integration of the cells into the vehicle. Although 2170 battery technology has improved since 2019, we think that Tesla's got the potential to hit around 300 watt-hours a kilogram for the next generation of batteries. One major way Tesla could achieve this is by incorporating more silicon into the battery's anode. Tesla recently filed a patent related to enhancing the 4680 by adding silicon to the anode, although silicon could cause issues with expansion and cracking the anode material. This could lead to faster charging and higher energy density, but might impact battery longevity. Some new tech, such as the highly elastic binders and new electrode designs, could help address this issue. According to a report by James Ma on X, the second-gen 4680 battery in Model Y has a small amount of silicon in the anode, and that shows an improvement from the first-generation battery. Some Model Y vehicles made in Austin still feature the 4680 battery, though with changes in the cathode chemistry and anode, the Gen 2 version of 4680 battery uses NCMA chemistry with a composition of 82% nickel, 11% cobalt, 5% manganese, 3% aluminum, whereas Gen 1 did have higher nickel and aluminum content and lower cobalt. The battery's anode is made using natural materials with a bit of silicon similar to Gen 1 to enhance battery performance by increasing safety and improving overall efficiency. If Gen 2 had significantly improved over Gen 1, this full version will be even better. In fact, Tesla has not yet begun producing 4680 batteries with dry cathodes. They produced and tested these cells for about a week on the Cybertruck. The company has initiated testing of their vehicle with 4680 batteries featuring dry cathodes. Cybertruck's battery cells indeed contain a small amount of silicon in their anodes, and Tesla has mentioned the potential to increase the battery range by 20% due to the integration of silicon in the 4680 battery anode. This could be a major breakthrough if Tesla's predictions come true. A recent Tesla patent describes the method for multi-layer electrode films, where the main issue is the poor adhesion of the active material layer layer like graphite to the metal foil, leading to electrical loss and reduced storage capacity. Silicon, despite its high energy density, encounters issues with volumetric expansion during battery cycles, and that makes it challenging to get that long-term performance. This patent proposes a multi-layer approach, with a silicon-rich layer in the middle and higher adhesion layers on the top and bottom to maintain the stability of the active electrode structure, and that improves connectivity and minimizes separation inside the battery. However, traditional wet processes do not support the multi-layer design as easily as Tesla's dry process. Wet film formation processes, including spraying, slot die coating, extrusion, and printing, can limit the ability to combine active layers and face challenges in achieving uniform material dispersion. Additionally, wet processes are often costly and require time-consuming drying steps, and that can be problematic as the electrode film gets thicker, leading to limitations in the thickness of films produced using wet processes. How has Tesla thoroughly resolved the issues with the 4680 battery? Reports have come out that Tesla's new dry electrode process has finally resolved the issue and could increase the energy density of the 4680. According to sources over in China, if energy density increases by 20%, the 4680 battery becomes the highest energy density battery worldwide and could be produced at scale. Currently, dry cathode technology is not available to automakers, but this means Tesla's production costs for Cybertruck are going to go down and its range will go up substantially. Tesla has finally addressed the issue with a 4680 battery that they face with dry cathode technology. So, what does all this mean? Tesla introduced the first dry cathode for the Cybertruck in July and began testing vehicles with their self-produced 4680 dry cathode batteries. This is a big-time milestone in improving technology and cost efficiency. However, we do remain surprised that it took longer than expected. We don't understand why it actually took years to complete. This means that the battery will be much cheaper for Tesla to make. The major difference between dry and wet cathodes is production cost. And we know you're curious about why dry cathode technology is important for Tesla's batteries. First, let's consider the production costs. Traditional wet cathode technology requires the use of organic solvents such as NMP during production. After the cathode materials are mixed with the solvent, the mixture must undergo a drying process in large ovens to remove the solvent before the cathode layers are cut and then rolled. This process is energy-intensive and costly, with solvent and drying costs estimated to account for about 5 to 15% of the total production cost of lithium-ion batteries. In contrast, the dry cathode technology being developed by Tesla and other companies eliminates the need for solvents in drying processes. The cathode materials are directly mixed into a dry powder layer, which is then pressed and rolled without drying, significantly cutting production costs by up to 20 to 30% compared to traditional wet cathode technology. In addition to cost reduction, dry cathode technology has the potential to improve production efficiency. By eliminating the drying process, production time gets shortened when that speeds up manufacturing. This is particularly important for Tesla as the company scales up 4680 battery production to meet the growing demand. Moreover, removing NMP solvents not only saves costs but also improves the air quality in the factory and reduces waste disposal costs, as NMP is a hazardous substance that has to be handled carefully. The use of NMP in wet cathode technology is not only expensive but also has negative environmental impacts. NMP is an air and water pollutant, requiring pollution control and waste disposal measures, which adds to the cost and environmental impact. On the other hand, dry cathode technology, by eliminating the need for solvents and drying processes, significantly cuts carbon emissions and energy consumption in battery production. This aligns with Tesla's goal of reducing the environmental impact in its products and production processes. In practice, when Tesla acquired Maxwell Technologies back in 2019, a company specializing in dry electrode technology, it demonstrated Tesla's serious commitment to developing and implementing this technology. Elon mentioned that adopting dry cathode technology is a key part of Tesla's strategy to make cheaper and higher capacity batteries for its EVs. While Tesla's electric trucks are currently being delivered, they don't feature dry cathodes. These batteries are not inferior products, but they are more expensive for Tesla to make. A report from a Chinese publication indicates that the 4680 batteries used in Cybertruck's production currently have a cathode produced using Tesla's dry electrode process and then an anode sourced from a supplier. This means Tesla no longer longer has to buy anodes from suppliers but can make them using their own dry electrode process, and that significantly cuts down on production costs. It's estimated that those production costs will decrease by around 10 to 15%, which, while not substantial, is still something. If Tesla can incorporate more manganese or silicon into their batteries, energy density will increase. Reports from sources familiar with the issue indicate that Tesla is aiming to start mass production of complete 4680 batteries by the end of the year, with both anode and cathode produced using the dry electrode process. This could increase energy density, although the exact amount is yet to be determined. Some sources suggest this could increase the energy density of the 4680 battery by 20%. If that's true, Tesla could improve the range of Cybertruck to around 400 miles, and that's a game changer. This means Tesla could use a much smaller battery pack than its competitors while still achieving the same range, reducing cost per vehicle and maintaining a significant advantage in electric vehicle production. Stay tuned and see if this holds true, and let me know what you think in the comments. What is the impact of reducing the production costs of the 4680 battery on Tesla vehicle prices? Reducing the production cost of the 4680 could have profound impacts on Tesla's vehicle pricing and the company's financial performance. 4680 is an advanced battery technology that Tesla's adopting to improve performance and reduce the cost of electric vehicle production. In the context of increasing competition in the EV industry, lowering battery production costs could offer significant benefits to Tesla, not only in terms of pricing but also in competitiveness and profitability. First, reducing the cost of making 4680 batteries could lead to a decrease in the retail price of Tesla models. Yes, please. According to projections, if battery production costs are cut by 30% from 100 kilowatt hours to $70 a kilowatt hour, each vehicle using a 100 kilowatt hour battery could save around $3,000 just from the reduction in battery costs. Given that batteries account for 30 to 40% of the total cost of making an EV, this cut could lower the overall production cost of a vehicle by up to 10%. This means the production cost of a Tesla Model 3 could go down from about $35,000 to $30,000, and that's equating to a savings of about $5,000 a vehicle. Reducing battery production costs could also enable Tesla to lower the retail price of its vehicles, making its models more attractive to consumers. If Tesla does indeed decide to reduce the price of the Model 3 from its current level of $39,900 to about $34,490, this could not only attract more customers but also potentially increase sales by 15 to 25%. A lower retail price could create a positive shock in the market, helping Tesla expand its market share and strengthen its presence in the mid-range electric vehicle segment. On the other hand, if Tesla chooses not to alter the retail price and keeps vehicle prices as they are, cutting production costs could also provide other benefits. The savings from reduced battery costs could enhance the profit margin on each vehicle, giving the company additional capital to invest in research and development of new technologies. Tesla could use the savings to expand production lines, research new battery technologies, or develop new vehicle models. This could help the company maintain its competitive edge and lead the electric vehicle industry. Overall, reducing the production cost of the 4680 battery could provide multiple benefits for Tesla. First is the potential to lower the retail price of vehicles, making them more attractive and boosting sales. Second is the increased profit margin per vehicle if retail prices stay unchanged, allowing the company to invest further in technology and product development. These impacts could not only improve Tesla's financial performance, but also strengthen the company's competitive position in the EV industry, providing long-term benefits for both the company and us consumers. What improvements have been made at Tesla's 4680 battery manufacturing plants? Tesla's approach to boosting 4680 cell production involves a multifaceted strategy focusing on significantly expanding gigafactory facilities and optimizing the production process. This comprehensive effort is evident through the development and expansion of key production sites, notably Gigafactory Texas and Gigafactory Berlin, as well as the implementation of advanced technologies to streamline the process. Tesla's expanded its Gigafactory facilities to enhance 4680 cell production. Gigafactory Texas, the cornerstone of this expansion, spans approximately 2,500 acres, making it one of Tesla's biggest and most advanced production sites. The facility is designed with a vast production area of about 10 million square feet, featuring numerous production lines dedicated exclusively to 4680 cells. The site represents a major step forward in increasing production capacity and includes advanced automation and robotic systems to streamline the production process. By early 2024, Gigafactory Texas is expected to achieve an impressive annual production capacity of 100 gigawatt hours for 4680 cells. Recent upgrades include the installation of high-speed electrode coating machines, which help accelerate production speed and consistency, reduce production time, and improve overall efficiency. Regarding Gigafactory Berlin, this facility is strategically positioned to serve the European market and is equipped with advanced manufacturing technologies. By the end of 2024, Gigafactory Berlin aims to produce 50 gigawatt hours of 4680 cells annually. This ambitious goal reflects Tesla's commitment to meeting the increasing demand for high-performance batteries in Europe. The factory combines advanced European manufacturing standards and is equipped with automated systems to ensure high-quality production. Tesla's focus on optimizing the production process is a crucial component in boosting 4680 cell output. Data analysis and AI play a key role in this optimization effort. Data analysis is vital for monitoring and refining the production process. By tracking machine performance, raw material quality, and production line efficiency, Tesla can identify bottlenecks, anticipate potential issues, and implement corrective measures quickly. Predictive maintenance, driven by historical data and real-time metrics, helps minimize downtime and ensures continuous production. This proactive approach allows Tesla to address problems before they escalate, maintain smooth operations, and reduce production disruptions. Quality control is another important area where data analysis contributes to optimization. Advanced data analysis enables early detection of defects and ensures high standards for cell quality. By analyzing data from various production stages, Tesla can identify patterns and anomalies that may indicate quality issues. This allows for timely adjustments and improvements, ensuring that the final product meets the company's rigorous quality standards. AI further enhances production optimization by improving scheduling, inventory management, and streamlining supply chain operations. Machine learning models play a crucial role in refining the production process and enhancing overall efficiency. AI-driven automation handles tasks such as cell assembly and testing with high precision and speed, reducing human error and increasing production throughput. Additionally, AI supports supply chain management by forecasting demand and optimizing inventory levels. This helps prevent delays, reduce costs, and ensure that production lines have the necessary materials and components for smooth operation. Despite significant progress, Tesla faces several challenges in boosting 4680 cell production. One major one is managing the supply chain for specialized raw materials used in battery production. To address this, Tesla's formed strategic partnerships and invested in raw material processing facilities. These efforts aim to ensure a stable supply of critical materials and reduce reliance on external sources. Maintaining high-quality standards is another challenge that Tesla addresses through ongoing technological improvements. Advances in electrode materials and battery chemistries play a huge role in driving 4680 battery technology forward. For example, improvements in electrode materials and electrolytes contribute to enhancing performance. We hope you'll experience the utmost relaxation after watching this video. If you do, please press the like button and join your Tesla Car World community by subbing to our channel. Smash that notification bell and stay tuned for any fantastic videos coming your way. Your feedback and time are highly appreciated. Thanks for watching, and we look forward to seeing you soon. Take care and God bless.